Hello, everyone. Whoa. My name is Patrick Clay, and I'm an engineer working on Google Cloud Dataproc. I'm here today to demonstrate to you how you can use Apache Spark MLlib on Google Cloud Dataproc to gain insight into your data, to train models, and then to deploy those into production. I know that you've heard a lot about machine learning on the Google Cloud Platform over the past couple days, but I hope by the end of this, you will walk away thinking that Spark MLlib is a tool that you should be excited about and consider trying, if you haven't already. My talk will primarily be a demo of Spark MLlib on Google Cloud Dataproc. But before that, I wanted to introduce the tools that I'll be using in the demo, not just MLlib and Dataproc, but BigQuery and Cloud Datalab. And at the end, I'll try to wrap things up and make comparisons to our new suite of machine learning offerings. So before I dive into this, just so I can have a sense of the audience, could I see a show of hands who has used the tools that I just mentioned? I'll mention them again. Who's used BigQuery? OK, quite a few hands. Cloud Datalab? Couple. Dataproc? Getting a couple. And Apache Spark, either on Dataproc or elsewhere. OK, that's a lot. Guess that's why you're here. So doesn't need too much of an introduction based on your hands, but BigQuery is the oldest and possibly most popular data processing tool on our cloud. It's our one-stop data warehouse and SQL engine, and its best use case is scaling your queries from megabytes to terabytes, even to petabytes if you need, without ever worrying about configuring resources, setting indexes, just scales as you need. It's what I like to think of as interactive speed, that when you're in the BigQuery console, you can just write a query, and before you have to switch tabs, certainly before you have to walk down the hall to get a coffee, your query runs. However, the world isn't all SQL, and sometimes you want to do things like machine learning. So that's where Cloud Datalab comes in. Datalab adds a bunch of rich features to Google Cloud storage services like BigQuery. So it can take data from Cloud SQL, Cloud Storage, BigQuery, and then process that data inside of a Jupyter-based cloud notebook with all of your favorite Python data processing libraries, pandas, NumPy, SciPy. You can also process them on cloud distributed processing engines like Dataflow, Dataproc, or now ML Engine. If you want to do machine learning inside of Cloud Datalab, it has TensorFlow and scikit-learn, and it has really nice visualizations. OK, so we're here to talk about, or I'm here to talk about Apache Spark, which I think combines a lot of the best aspects of BigQuery and Datalab. You might think of Apache Spark as just a general distributed processing engine on the JVM, like a Hadoop MapReduce, but maybe a little more memory optimized, maybe a little more higher level, like Apache Beam. And that's all true. But really, in the last 2 years, Spark has tried to differentiate itself by adding layers on top of its base processing engine, the first being Spark SQL. And I really like Spark SQL because I like processing in SQL. I like data frames. In Python, I like using the pandas library or NumPy. So when I'm using Spark, I almost entirely use some form of Spark SQL. MLlib, the machine learning library I'm here to talk about, is now currently almost entirely based on Spark SQL. So if you can write SQL, if you can use data frames, you can use MLlib. MLlib, like I said, is the machine learning library. Its API was inspired by scikit-learn. And it is many, many machine learning algorithms. It has kind of all of your classics, linear and logistic regression, k-means clustering. It has kind of your workhorse algorithms, like random forests or simple vector machines, and even some esoteric algorithms like latent Dirichlet analysis, or allocation, rather. But there's more to machine learning than running algorithms. You have to convert your data from whatever form you find it into standardized features. And this is another place where MLlib shines, because it's based on Spark. And Spark is, first and foremost, a data processing engine. So it's really simple to take raw text data, convert it into initially numeric data, and then vectorized data. All of those transformations are built in, very easy to use. Once you have your transformations and your algorithms, you compress them together into pipelines, which you run to train models. And then you can improve the models with hyperparameter tuning. And I will show you all of that in the demo. Unfortunately, Spark can be a little painful to use. It requires, at the very least, a cluster of machines, which Google Compute Engine can provide. But then you have to install the software, configure it, all of these things. So that's where Google Cloud Dataproc comes in. This is the product I work on. And it provides a fully managed cluster running Apache Spark, Apache Hadoop, Pig, and Hive. And on top of these, it adds the cloud storage file system so that you can keep all of your data in GCS. Don't have to worry about maintaining your cluster. And BigQuery connector for structured data. One of kind of the lesser known features of Cloud Dataproc is being able to mix in many different things, but certainly cloud notebooks. So I already mentioned Datalab, but there's also Apache Zeppelin, which came out of the Spark community, and Jupyter, the original notebook, as it were, which work really well with Spark because Spark is so memory optimized that just like BigQuery, if you're sitting in that interactive cloud notebook environment, you just run a couple lines of code and see your results within seconds. Dataproc is really fast. You can get it if you want a 10-node cluster, you can have it in under 2 minutes. If you decide 10 nodes, 10 VMs is enough, you can have 100 VMs in another 2 minutes. The configuration means it's really easy to use. You just say, I'd like a cluster. If you want to do more configuration, you can do that. And lastly, and most importantly, it's ephemeral. So all of your data stays in a cloud storage service, and you don't have to worry about it. So how does this all fit together? So that's quite pale. But the Datalab runs inside of a Docker container on a Compute Engine VM inside of the Dataproc cluster. Datalab uses Spark's Python, PySpark APIs to access Spark across all of the nodes of the cluster. And both Spark and Datalab access Google Cloud services, such as Cloud Storage and BigQuery. The user accesses Datalab just as they normally would when running on GCE. So without further ado, let's switch to the demo. Show this. Cool. So this, as most of you who raised your hands should recognize, is BigQuery. And today I will be looking at the New York City Taxi and Limousine Commission Yellow Taxicab dataset. It's one of my favorite public datasets on Google Cloud. We have quite a few, mostly on BigQuery, which you can see here. Some in Google Cloud Storage, and now some on PubSub. If you saw the keynote yesterday, you saw a demo of using BigQuery, Dataflow, and ML Engine to analyze people who are coming from airports and near food for advertising purposes. It's quite slick. Today I'm not interested in such a specific question. I have a broad question. Where are people in New York catching taxi cabs? Specifically, at a given time on a given day of a week, where in New York are taxi cab pickups happening? So I don't need this entire data set, which is why, where's my cursor? I will run this query to filter out only select the pickups. And it's important that I filter this data, because one nice thing in BigQuery is you can preview your data, and you'll notice that there's a lot of problematic entries in any data set, but certainly a free data set, has all these zeros. I don't want to train my model on taxi cab pickups off the coast of West Africa. So clean my model and put it in this taxi cab data set, which you'll see still has 1 billion records, even after that filtering. And we need somewhere to process this. So I will use my terminal to spin up a Dataproc cluster. Normally, I would use the Cloud Console to spin it up, and but not all these flags are available. This is a 20-node cluster because why not? I can scale out. This is an initialization action, which is like a Google Compute startup script, except you can specify more than one of them. And this particular one installs Datalab. You can specify both of those inside of the Cloud Console, but I had a JavaScript issue with one of my libraries, so I am using I'm telling the initialization action to use a different Docker image than normal, but essentially just regularly running the initialization action. One sec. So Datalab, when running on GCE, opens a web server, a web UI, inside of the cluster. And I need to be able to access that from outside of the cluster. So our suggested way of doing that is to SSH into the cluster. And create an SSH tunnel. You could also open ports in your firewall, but that's considered less secure. And so I do this instead. And now, in yet another terminal, I have too many terminals, I can open a special Google Chrome that is configured to use this proxy. And where is that? Oh, that's on my other screen. And I bring that over. And if I can still find my first terminal, we're still deploying the cluster. I said it takes 2 minutes. It takes a little more than 2 minutes if you're running initialization actions. There we go. So now, hopefully, I go to welcome to Datalab. Very important note, Datalab is no longer beta. This doesn't apply anymore. Datalab went GA this week, are generally available. But like I said, I was using an old Docker image. You can load notebooks into Datalab a number of ways, but I'm just going to load one from my machine. So if I upload my Python notebook, and double click on it, hopefully. OK, this is a Datalab notebook. If you're at all familiar with Jupyter or Zeppelin or even MATLAB or Mathematica, you'll be familiar with these cell kind of notebook things. The first thing I'm going to do, kind of as a preamble, is to install a Google Maps visualization library that I'll use later. But I wanted to do that, get that out of the way. And it's not a good sign. Oh, there we go. all good. And just reloads, so it loads the JavaScript. OK, on to the rest. So the first thing you have to do when data processing in Spark is load data, and it's not glamorous. So I'm just going to try and get it all the way at once. But you can see that Datalab has provided very convenient Google Cloud Storage and BigQuery library or APIs that allow me to extract the table that I just created in BigQuery as compressed CSV in Google Cloud Storage. And when that finishes, we will be able to load it into Spark. And because we are using Spark's SQL and data frames, we can just infer the schema from that CSV record, except that there's a bug and the dates don't get parsed correctly. So I have to do manual date processing. Oh, there we go. So I printed out the schema of my data frame. And you can see that the date column written here is a string. So now I'm converting it to a date in Spark, not at all interesting and not related to MLlib. Now I'm just previewing my data. One great thing about Spark is that you don't actually have to load all of your data in, at all to preview it. You can just look at a tiny piece. So that's what we've done here. I should have actually asked before. Is this legible in the back? OK, good. And so you see now we have a nice, when the taxi was picked up, where it was picked up, somewhere in New York, in the lat long. In Datalab, we can run queries against BigQuery. Also, in Spark, you can register SQL tables. So I'm just running a simple select count star against both BigQuery and Spark to make sure that I have all the data. It takes a long time in Spark because this data is still sitting in GCS. Spark is lazy, so until I say select count star, it will actually never load the data. Once that finishes, what I want to do is I need to bucket my data into the hour and day of the week so that I know, so I can ask the question, on a typical Thursday morning at 10 a.m., how many taxi cabs were there in New York City? And so this SQL query just buckets my data by hour, day of week, and city block, essentially, 1,000th of a GPS coordinate, or of a degree of latitude or longitude. So you can see we haven't lost any data. We have all of the records. And we can start machine learning. Oh, that needs to run. And, well, that's still running. While that's running, I'd like to introduce the Spark MLlib API. This MLlib's API is actually my favorite thing about it, beyond its convenience and its use, because I think it's really slick. There are 4 main classes in MLlib. Transformers, which take data and output new data. Really what they do is they all add a column to your data frame. So they just add a column to your SQL data structure. There are estimators, which take your data frame and output a trained model. So these are all the algorithms I mentioned, the regressors, the classifiers, the clusterers. Then there's the model itself, which takes your data and makes predictions based on it. And the really neat thing is predictions are just another column of data. And I said transformers are things that take your data and add a column. So models are transformers, which means that you can compose them in just a sequence of transformers and then an estimator. You fit it to get a model, and you keep transforming. The way that you compose them, or the best way, is inside a pipeline. And here's a picture from This is just from the Spark documentation. You can find it, just Spark ML pipelines. But setting taxis aside for a second, suppose you had some raw text, like, say, the works of Shakespeare. And you wanted to classify them into, say, categories, comedies, tragedies, etc. One way you could go about this is you take your raw text, you'd split it into words, or possibly n-grams, depending on your model. Then you need to somehow convert these words into some kind of numeric feature vector. And then finally, you train an estimator on that. So in this case, Spark provides just plug and play, a tokenizer, many different things, but a hashing transform, and a logistic regression estimator. You put all of these together in a pipeline, and then you fit the pipeline, and you end up with your trained model that you can transform into predictions. So this is, again, straight out of the Spark's API documentation. But the high level is we create toy code, but it has this text column. We define these transforms and estimators all in like one line of code, and throw them together into a pipeline, fit it to our data. We get a model. You run the model, or you create toy test data, and then you transform the model to get predictions. So really, in this case, it's a very glorified word count. The data is designed so that Spark is, if the data contains the word Spark, it's 1, otherwise it's 0. But in general, you could do more fancy transformations like topic determination in the Shakespeare example. So if I scroll back up, the last thing I said with my pre-processed data was that I'd like to describe it. I know this top column is quite faint. But here's the final state of our data. There's the hour in which the hour in the day between 0 and 23, in which it was picked up, the day of the week, 1 being Monday, 7 being Sunday, and our latitude and longitude, bucketized, so rounded to the thousandth. The count of the number of pickups in this region, and then just because it's kind of unreasonable to train a model from 1 to 5,000, I took the log of that, so it's between 0 and 11, which is more manageable. So now let's actually do some machine learning. So this should look very similar to the text processing example, except we don't need to do much transformation because I chose to use a random forest regressor. And one of the wonderful things about random forests is they don't require much preprocessing. They can take numeric data. They don't need normalized or categorical or fancy transformations, which Spark MLlib can all do. So all I do is take the columns that I'm interested in. I put them in a vector called features. I tell the regressor, look at the features and try to predict the label column, which is that log space feature column, and run predictions. And if I run that now, we get some predictions. So some of these are pretty good. There's only one pickup here, and predicted a very low amount. This is pretty perfect, 1 for 1. But some of them are pretty not so great, like this one. So let's be more specific. I didn't mention evaluators in my ML classes, but they're also very important. So you can take the evaluator and find that our R² value is about 1/2, and our root mean squared error is about 1.5. So in layman's terms, I mean, the root mean squared error means that in logarithmic space, we're off by usually about 50%. So if there were 6 passengers, we might think there's between 4 and 9, which isn't too bad. Or sorry, not 6 passengers, 6 taxis leaving in that hour. But I still don't have a great sense of how good or bad our model is. So what I'm going to do is rely on Cloud Datalab's visualization capabilities and sample both the real data and simulated data, where the simulated data takes the number of pickups that we predicted and randomly generates them inside that bucket. So this is the Google Maps library that I loaded at the beginning. And it forms a very nice Google Maps heat map. So this is what we predict during, let me scroll up, rush hour at Thursday. We seem to have found Manhattan, which is good. But we have a lot of pickups in the middle of the East River, and it's generally kind of messy. If you compare this to the real data, you'll see this is very nice and pretty, because that's what the real data is. It's all in the streets. LaGuardia is all nice. So clearly, we have some work to do. We can also look at the middle of the night, again on a Thursday, and it really is no better, whereas reality is, again, quite nice and clean. Also, in real life, less people are catching taxis in the middle of the night on a Thursday, but we didn't really learn that. So how do we improve our model? So every estimator, but also pretty much every class in MLlib has this extract param map method where you can look at the parameters inside of it. So this is what our random forest regressor ran with in the default parameters. I'll draw your attention to the trees are only of depth 5. Oops. Trees are only of depth 5, and there were 20 of them. Not much of a forest, and not much in terms of trees. So we could go and rerun the code with a deeper tree, or more trees. But then we have to worry about overtraining and all of these things. So really, the trick is to let Spark do the work for you and set up a parameter grid and say, please consider trees of depth 5 and 15, and trees of 5 and set the number of trees to both 5 and 20, build this whole grid, and then evaluate it. There are a couple different ways to run all of your grid. I used a train validation split. You could also use cross-validation. It's not a big deal. This is one case where Spark does take a long time, which is why I kicked off all my data processing beforehand. Cross-validation takes a long time because as a general rule, Spark will never transform the same data twice at the same time. And so, unfortunately, when you run your parameter grid, it will only ever use one piece of the grid at a time. And if you've scaled out as I have, it's pretty fast, but it's still not great. So with this, I took the best model and evaluated it on my validation data. And we got a better R-squared, 0.73. Not the best. But our root mean squared error is now getting more reasonable. And if we go back and look at our models, we can re-simulate the data. And now this kind of looks respectable. We don't have pickups in the middle of the East River. Usually we have pickups at LaGuardia. OK, that was bad. Should have fixed the seed. Anyways, but we found Manhattan much better. And it looks much more like the real data. Same with midnight. We still think that there are more pickups than there are, but at least they're at reasonable locations. And for the sake of time, I didn't set a huge parameter grid or super deep trees. But if you train on all of the data with super deep trees, or trees of depth 30, which is the deepest Spark goes, you can get up above 90%, or an R-squared value of over 0.95. I kind of glossed over splitting the data into test, validation, and training, but I did. And here's the actual test results. And they're exactly in line with our validation, which is good. We didn't overfit our model. And pretty much everything I've done here could be done on any Spark cluster on GC, assuming you had one. But the last great thing about MLlib is the ability to take models and reuse them later. So if you've seen talks on ML engine and version models and storing models in the cloud, this isn't exactly that, but it's somewhat similar in that we can take the model that we just trained. I don't even know what this model is. It's the best model that that grid put out. And write it out to GCS and take any data, but in this case our test data, write that also out to cloud storage. And then after tearing down our cluster in another cluster a year from now, we can just load the model, load our data, run our predictions, write them out again, evaluate them, do whatever we like. And at least these four are completely agnostic as to what we did in our data processing. All I know is that I made a Spark MLlib pipeline. But these 4 lines of code are absolutely reusable over and over again. And to demonstrate that, if I go back to one of my terminals, actually, if I go back to my other Chrome browser, I have this file in GCS called predict.py. And it just does those 4 lines. Load a model, load some data, transform the data using the model to make predictions, save that out to cloud storage again. And I can submit this as a one second. I can submit this as a job to Cloud Dataproc using the Jobs API. And the Jobs API, if you've used Spark, this is essentially the same as running Spark submit on a Python application. There's too much log spam that I should filter out. But, and I'm running on. Actually, I was running that on the same cluster. I'm going to run that on a different cluster to demonstrate that I don't need to know about anything that went on in that cluster. This is an entirely separate cluster. You can't really see that, but it is. And there we go. And now it will take that data, transform it, write those predictions out, and you could use those predictions somewhere else. So if you were using Cloud Datalab or any notebook, generate a model in an interactive kind of ad hoc exploratory way, you can save that model, send it off to another engineer, another team, doesn't matter. Use that model over and over again. And that is really a lot of log spam. But it says right there, finish with predictions. If I can, which was the all done, successful job. And that's all I have in the demo. So if we could go back to the slides. OK. To wrap things up, hopefully you just saw how Spark and Dataproc can leverage Spark SQL to do very useful kind of ad hoc data processing, MLlib to take that data processing and add very simple 3-line machine learning APIs on top of that. When you use it with Datalab, you get that interactive just run, go back and edit your parameters options. Or you can use parameter grids so you don't have to. And that beautiful visualization of Google Maps, Google Charts, and other things. And lastly, with the Dataproc Jobs API, you can take all of your trained models and reuse them elsewhere. So I promised I'd talk about other machine learning offerings, compare and contrast them. So what about Cloud ML Engine? It's similar to MLlib in many respects. You train your models in a distributed fashion. You can persist the models for later use. And the high-level API of TensorFlow, if you went to the talks, or one of the high-level APIs, is called tf.learn. Both tf.learn and MLlib are both based on scikit-learn. So a lot of the estimator model, that should all feel pretty similar between the two. There are some differences, but it should be pretty much the same. However, they do each have key strengths. ML Engine was written for TensorFlow. It is TensorFlow. So and TensorFlow was written first and foremost for deep learning. So if you want deep learning, highly recommend TensorFlow and ML Engine. Spark does have deep learning. They do have neural nets, but it's been, or MLlib does, but it's been, it's not its intended first-class purpose. ML Engine is serverless. I'm sure you've heard that word a lot recently. Dataproc is not. Dataproc, you don't have to maintain a server. You can spin one up, take one down, but you do have GCE VMs. And there's advantages to both ways. One of the advantage of being serverless is a user with a cell phone can, or a client on a cell phone can make a call to the prediction API. You don't have to worry about managing infrastructure at all. The advantage of having the cluster around is you can have your data cached in memory in Spark, and you can do that kind of ad hoc, iterative, exploratory analysis. Furthermore, you can do the kind of general Spark processing or pre-processing on your data. So all of that kind of painful SQL munging I did at the beginning, you could do in Dataflow or Spark and Beam and then run on ML Engine, but it's all sitting there for you with Spark on Dataproc. And the last key advantage, or I already mentioned the interactive speed of the cache memory. The last key advantage of MLlib is that all of the APIs have 10 parameters. You don't need to specify them. They work out of the box. You can auto-tune them, and they can be written in like the 4 lines of code that I showed at the very end. The last similarity that I didn't mention when I was mentioning the similarities is that both are built on open source. So at the keynote today, there was a lot of talk about how TensorFlow is in many respects one of the hottest open source projects out there right now, certainly if you look at GitHub statistics. Well, when I checked, Spark and TensorFlow are the 2 most forked GitHub projects. So they're both very similar in that respect. And they're both still getting an incredible amount of commits. TensorFlow just went 1.0. Spark went 2.0 last summer, but is continuing to iterate and evolve. So it's kind of really an exciting time to be using either tool. And with ML Engine and Dataproc, you constantly leverage all of the improvements that are being driven in both communities. So that's essentially all I have. If I've encouraged you to go try any of this out, I have some helpful links. My demo is not available on any of these links, but it will be. At some point, these slides will be available, I believe. and the demo should be linkable through one of the quick starts, or the Cloud Dataproc quick starts. We also have tutorials, the initialization actions, including the Datalab one I demoed. There's resources on Spark ML and Cloud Datalab. And lastly, for the New York City taxi dataset, if you, I mean, you can go and look up our version of it, but if you just Google New York City taxi dataset, you can find lots of great and interesting other data science projects that people have leveraged it for, and that might inspire you. These links are, well, also possibly helpful if you get stuck on any of the quick starts. They're mostly Dataproc specific because they route to me. The Stack Overflow also has the Apache Spark MLlib.